Let's look at a physics problem that involves several areas of physics. So here is an apparatus, and the problem states the following. Suppose you have a 1 kilogram beaker containing 2 kilograms of oil, and the density of that oil is 916 kilograms per cubic meter, and it's resting on a digital scale, as you see there. Now, a 2 kilogram block of iron is suspended from a spring scale and is completely submerged in the oil. The question is to find the equilibrium readings on both scales. So let's see how that is done. So first, let's consider only the spring scale and the iron mass. Let's isolate that part of the problem. So the mass from the problem said it was 2 kilograms, and so its weight is that 2 kilograms times the acceleration of gravity. And what we do is we get negative 19.6 newtons. The acceleration of gravity is negative 9.8 meters per second squared, and so the weight of this object will be negative 19.6 newtons. Now we say that the system is in static and dynamic equilibrium. What that means is that the system is not moving up or down, and that all of the forces are balanced. That is, the upward forces and the downward forces are equal in their magnitudes. So to make this a little simpler, we can draw what's called a free body diagram. We have the black dot where we're going to pick a point where all of the forces will be acting. We have an upward force, which is the tension in the spring of the spring scale. We'll call that T for tension. And then the weight, mg, will be going downwards. The equation for dynamic equilibrium is sigma F, or the summation of all the forces, equals 0. So we simply add up all of the forces, T plus mg, and set that equal to 0. Now, doing a little algebra, we subtract the mg from both sides, and we get that T is equal to mg, but we have a negative sign in front of it. Now, since we calculated earlier that the mg for this iron is negative 19.6 newtons, if you take the negative of that, you get that the tension is 19.6 newtons. And remember that a newton is a kilogram meter per second squared. So now let's take this apparatus and include the oil on the spring scale. Okay. What just happened? Well, if you noticed, the little red marker on the spring scale actually moved up a little bit. So we say that the upper scale decreases. But one thing that is not noticeable on this diagram is that the lower scale will increase. In other words, if we were able to measure the oil in the beaker before we put the iron inside of it, it would be a certain reading, but when we put the iron inside of it, that reading will increase. So why does all of this stuff happen? Well, first off, the upper scale decreases because the iron is actually lifted up by a force called buoyancy. We say that the oil buoys up the iron or lifts it up a little bit. And so that's why the spring scale goes up a little bit. Now the lower scale increases because that buoyant force, which is going up, has to be balanced by a reactive force going down. That's Newton's third law, that for every action there's an equal but opposite reaction. So we say the lower scale increases because the system is in dynamic equilibrium, and the upward force, that is the buoyancy, must be balanced by the equal downward force. We'll call that the reactive force. So let's look at the details of this. First off, the formula for buoyancy is B equals Greek letter rho times V times the absolute value of G, and I'll explain the absolute value in a moment. B is the buoyant force, that is the force which lifts up the iron, as the blue arrow shows there. Greek letter rho stands for the density of the fluid that's doing the buoying. And from the problem, you may remember that the density of that oil is 916 kilograms per cubic meter. Now the volume V is the volume of the displaced fluid. In other words, when you put an object in a fluid, it displaces or moves the fluid away from it, and so that's the displaced volume. So for this particular problem, it's an interesting problem to solve because we don't know the shape of this iron. Is it a cylinder? Is it a rectangular solid? Is it a blob? We don't really know what the shape of that iron is, and so we'll have to do an interesting trick to calculate that. And of course, the G is the acceleration of gravity. So first of all, let's see how we get that displaced volume. Well, one thing that you can know is that the formula for density of anything is equal to its mass divided by its volume. So if we take that formula and do a little bit of algebra on it, we can solve for the volume and say that the volume is equal to the mass of something divided by its density. So for this iron mass, we can say that the volume of the iron is equal to its mass divided by its density. Now remember that from the problem we saw that the mass of the iron was 2 kilograms. And then if we look up in a table or go online and get the value, we find that the density of iron is 7,860 kilograms per cubic meter. If we do that division, we find that the volume of that iron is going to be 2.5 times 10 to the negative fourth cubic meters. So let's go ahead and calculate the buoyancy. We simply plug in the values of the density, which is 916 kilograms per cubic meter, the volume, the displaced volume, 2.5 times 10 to the negative fourth cubic meters, and the absolute value of negative 9.8 meters per second squared. Now the reason I'm using the absolute value is that I want this to be an upward force. When we do that math, we see that it is 2.28 kilogram meters per second squared. Of course, a kilogram meter per second squared is a Newton, so this is 2.28 newtons. Now if you go back to that free body diagram that we saw earlier and add in the buoyant force, we now use again the equation of dynamic equilibrium. The sum of the forces equals 0. So T plus B plus mg equals 0. Doing some algebra on that, you see that T equals negative mg minus B. Well, the weight, remember, was negative 19.6 newtons since it's pointing downwards. And so the negative of that is positive 19.6 newtons. The buoyant force was 2.28 newtons, and so the negative of that gives us negative 2.28 newtons. So doing the subtraction, we see that the tension in the spring went from 19.6 to 17.32 newtons. And so that's the reading on the spring scale. And if we were able to look at it closely, you would see that that's what it reads. Okay, so we've got the upper scale. Let's see what the lower scale reads. Again, from the problem, you know that the mass of the beaker is 1 kilogram. The mass of the oil is 2 kilograms. So the weight will be the addition of those two times the acceleration of gravity. So the weight is negative 29.4 newtons. And that will be a downward force. Now the reactive force is simply the negative of B. So if B was 2.28 newtons, we're going to subtract or make that negative so that it goes down like so. Now we're going to have one more force, and this one may not be so obvious, but it is the force that's pushing up from the surface of the spring scale. We call that a normal force, normal meaning perpendicular to a surface. And so that's going to be F sub n. And that force is going to be the force that the scale reads. So once again, we write down the formula for dynamic equilibrium. The sum of the forces equals 0. That is, the normal force plus the weight plus the reactive force equals 0. Do our algebra and say that the normal force is negative weight minus the reactive force. Plug in the values, switch the signs because both the weight and the reactive force have a negative sign in front. And so basically we're adding those values. And we get positive 31.68 newtons on the digital scale. And that's what it would look like. So the answer to this problem is that the spring scale would read 17.32 newtons, and the lower scale, the digital scale in this case, would be 31.68 newtons. Well, I hope that you enjoyed that presentation, and I thank you very much for watching.